In the previous video, we looked at how to find the reactance of the components of our circuit, and this is exactly the same circuit we used, and we determined what the reactance of our inductor was and what the reactance of our capacitor was in the previous circuit. So remember, we had a 3 ohm resistor that we still have here. Our inductor reactance is 7 ohms. We took the value of the inductor and multiplied it by the 754 radians per second that we found in our equation. That's our angular frequency. And we multiplied that same frequency by our capacitor value and then inverted, and that gave us 3 ohms of capacitive reactance. So in order to solve for the current in our circuit and the individual voltage drops in AC, we're going to use phasor math. And remember, to find the phasor for our sinusoidal equation, we need to find the RMS voltage and we need the angle. Okay, so the first step is we're going to find the phasor voltage. Okay, so find the phasor voltage and of course the impedances. All right, we found the reactance. That's what we have here. Reactance, which is the letter X. We're going to find next the impedances, which is the letter Z. All right. So first we're going to find the phasor voltage, and to do that we're just going to find the RMS voltage from the peak. Remember, right here, this is our peak voltage, okay, or E peak or V peak, whatever you want to call it. So 70.7 is our peak voltage. So if we multiply that by 0.707, we get the RMS voltage, which is 50. There's no phase angle, there's no phase shift in our equation. If there were, we would have something after that 754t. There's nothing there. So that means that our phasor angle is 0. Therefore, our phasor supply voltage is just 50 at an angle of 0 degrees. Remember, that's a complex number written in polar form. Okay, that's where that comes from. And this is the phasor math that we're using. Okay, so next we want to find the impedances of our components. So our resistor, the impedance of a resistor is always R at 0 degrees. So for that one, that's pretty easy. It's just 3 at 0 degrees, and that is our impedance of our resistor. If we wanted to convert that to rectangular form, we would get 3 plus 0j. Okay, so these are exactly the same, the ZR here and the ZR here, but one is in polar form and one is in rectangular form. Remember, let me get rid of that. Remember, we remember that it's easier for us to add and subtract in rectangular form, and it's easier to multiply or divide in polar form. So that's why you might use one versus the other. And when we're trying to find series impedance, we're going to add those. So sometimes I'll just write them in rectangular form to start with. So your resistance is always going to be the X value, and the Y value is always going to be your reactance, either your inductive reactance or your capacitive reactance. Okay, so the real or X value is here is the resistor, and the Y value is either XL or XC or a combination of the two. All right, so find the impedance of ZL. So for ZL, anytime you have an inductor, the inductor impedance is going to be X sub L at 90 degrees. Okay, that's just for an inductor, you're going to have that positive 90-degree phase shift there. So ZL in this case, we found that X sub L is 7 Okay, the reactance is 7 ohms. So ZL is just going to be 7 at plus 90, or if we convert that, and that is of course in polar form, if we convert that to rectangular form, we get 0 plus 7J, okay? So it's a positive 90 here, it's a plus 7J here, okay? So that plus is our positive 90 degrees. And for the capacitor, remember the capacitor has a negative 90 degree phase shift. So there we're going to see your impedance of your capacitor is always going to be the reactance at negative 90 degrees. So in this case we have the 3 ohm reactance up here that we found. So we're going to have 3 at negative 90. That again is the polar form. And then if we convert it to a rectangular, we get 0 minus 3J. So the minus 90 correlates to our minus J. All right, so once we've found our individual impedances in series, we just add them together just like we added series resistors in DC. If you're not using a calculator, this is where I would suggest you use the rectangular form. If you're using your calculator, it really doesn't matter. So you would add your ZR, which is 3 plus 0J, plus ZL, which is 0 plus 7J, and ZC, which is 0 minus 3J. Remember, to add in rectangular form, you're going to add all of the X values, 3 plus 0 plus 0. And then you're going to add the Y values, 0 plus 7 minus 3 right here. And that gives you your X value for the sum. So what you get is 3 plus 4J in rectangular form. Okay, and once you've practiced a little bit, you'll see here in your series AC circuit that ZT is going to be R plus XL minus XC J. Okay, so you'll see that that works out that way, and you can it'll be a little quicker for you. Okay, so if we convert this from rectangular to polar form, and you can use your calculator for this, we get 5 at an angle of 53.13. I have previous videos where you can learn to use your calculator to do this, and if you need help with that, let me know. Remember, the equation to do that as well would be z equals the square root of x squared plus y squared, and the angle is the inverse tangent of y over x. Okay. Now we convert this to polar form because it's easier to multiply or divide with polar form, and next we're going to use Ohm's law, which of course means we're going to multiply or divide depending on what we're doing. Okay, so we're looking for the source current, I sub s, and remember current is just V over R, Ohm's law, right? So if we take our source voltage and divide by our total impedance in AC, this would be our equation. So we have our 50 volts at 0 degrees divided by the ZT we just found in the previous step. And remember, to divide in polar form, your magnitude will be the magnitude in the numerator divided by the magnitude in the denominator. So 50 divided by 5, which is 10. And then the angle is going to be the angle in the numerator minus the angle in the denominator. So 0 minus 53.13. So that gives us a negative 53.13. And this is, that is our source current. Now once we find that, so that means that our source current can be described by 10 at negative 53.13 degrees. And that current is going to be the same throughout my series circuit because it's a series circuit and everything you learned in DC applies to AC. The current's the same throughout. So I want to find my voltage drops across the resistor, the inductor, and the capacitor. And I'm just going to apply Ohm's law there. So V equals I times R, or in AC, V equals I times Z. Remember, Z is, whoops, Z is to AC circuits what R was to DC circuits, okay? The same thing. Okay, so we're going to multiply I times ZR to get the voltage drop across R. So remember, we just found that that was 10 at negative 53 degrees. Multiply that by 3 at 0 degrees. And when we multiply, remember, we're going to take our magnitudes, the 10 and the 3, and multiply those to get our new magnitude of 30. And then our angles we're just going to add. So negative 53 plus 0 degrees gives us our angle. And the voltage drop across R is 30 at an angle of negative 53.13 degrees. We're going to do exactly the same thing with our inductor and our capacitor. So the voltage across the inductor is the current through the inductor times the inductor impedance. So we've got the same current because they're in series, times 7 at 90 degrees. Again, 10 times 7 will give you the 70, and negative 53.13 degrees plus 90 degrees will give you the angle, the phase shift for the inductor voltage. And then for the capacitor, the same thing, same current. This time we're using the impedance of our capacitor. And when we do the math, we get V sub C is 30 at negative 143.13 degrees. You can also plug these into your calculator and see that VR plus VL plus VC does indeed equal your supply voltage.